In this presentation, we will learn how to calculate the reactions. When we calculate the reactions, what normally we will receive as an information in an exercise is a beam. A beam is this blue rectangle, and this beam usually will be supported, in our case, by two reactions. Reactions can be drawn in books with a simple arrow, like here, reaction 1 and reaction 2. And after we will have forces that will be acting, or loads. I will write them in yellow, that are loads, load 1, load 2. Those are punctual loads, it's a point. But also we have distributed loads that are like, imagine like a series of books that are located there. This load can be, for example, 2 pounds. This can be, for example, 4 pounds. And this can be, for example, 1 pound per feet. That means that if this distance is 2, the total load will be 2 pounds. Well, that's what we receive. In many books, you will have a rectangle that will be your beam, and instead to have a reaction like an arrow, you can have something like a triangle. In other books will be a triangle with a line, like in this case, or a triangle with a line and the sign of Earth. Also, you can have a triangle with 2 balls. It's like 2 wheels, the ground, and sometimes you have more indication about the ground. And this means that you have a beam that is attached, that don't allow the beam to move up and down, because there is a ground there, and it's not moving to left or to right. In this case means that the beam can move to the left or to the right, because there are 2 wheels, but cannot move up and down. What that means is like you have a bridge, and the bridge is attached to the ground, here very well attached, and because of temperature changes, this bridge can become a little bit bigger. Therefore, there is a flexible joint there that allows the beam of the bridge to move a little bit, to grow to the left or to the right. That is normally the way that is drawn, but it's not important. It can be this symbol, it can be an arrow. The important is that you have reactions. In our case, normally we will have 2 reactions. And the first is 1 and the second is 2 in general. That is what we receive. What we need to calculate? First, we need to calculate how much are those reactions. Remember, it's an object in the space. Forces are acting in this element. In our case, we have only 1 of 30. We have 2 reactions, and the sum of all forces, in this case, vertical forces, need to be equal to 0. Well, we need to know how much is R1 and R2 to do that. After we know that the sum of horizontal forces is 0, we don't have any horizontal force here. Well, it's not important. And we know that the sum of moments is equal to 0. What that means that this object will not be rotating in anywhere. If this object, we put that force and that object became like that, you see, became deformed, is rotating. And we don't want that. Well, the summatory of moments in any point will be equal to 0. Attention. I am explaining that the summatory of moments in any point here, 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 the sum is equal to 0. That doesn't mean that the moment in a point there is 0. No, it will be a different one. Well, when we have this kind of beams, our objectives is to know 2 things. One, what is the maximum shear, the force that will cut this beam in some way, vertically, there, and that is the shear diagram. And after, what is the maximum moment or rotation that that beam have? Why? Because when we have a beam, the 2 important things can happen. One, that break like that because of a force, or 2, that bend. Those are the dangerous things that can happen to a beam. We need to know where is the point where it's more possible that that break will happen, maximum shear and the maximum moment. And in order to do that, we do 2 diagrams. diagram of shear, and diagram of moment. However, in this class, we will not be working with those diagrams. I am drawing the diagrams there, and they are there because in the future we will be doing that. Well, how you will organize your job? You will take the page of the screen like I did and divide into parts. In this side, you will write your original exercise, you will calculate, you will just write the two reactions, and you will leave a space under that drawing to do a diagram that is called shear force and a diagram that is called bending moment. In the other side, in the right side of the paper, you will do all the calculations that you need to do. I like to draw again the diagram because sometimes the original diagram will change to calculate the reactions. In this case, it didn't change. As you can look, it's the same. The only change is that we have the answer there that we find with all these calculations. And after, under that one, you will do all the calculations. Okay, let's start. We have this beam, and this beam is in the space. It's located in the space, and there is one force that is acting that is 30 pounds. And there are two reactions that, in principle, we don't know what are the values. Those are two unknowns, R1 and R2. How we calculate how much is R1 and R2? We have three equations that we studied before. First, the summatory of vertical forces is equal to 0. In few words, 30 plus R1 plus R2 is 0. This equation is not helping because we have two unknowns and only one equation. We know that R1 plus R2 is 0, but we cannot know how much is R1 and how much is R2. Second, summatory of horizontal forces is equal to 0. This equation is not helping in this case because we don't have any horizontal force. We don't have a force like that. Number 3, summatory or sum of moments in any place of the beam is equal to 0. That will help us. Why? Because remember, when we calculate a moment, moment is force multiplied by distance. Well, the moment in this point will be a number that will be in this diagram here. And the moment in this point will have another value that is here. And it's a number that is not necessarily 0. In this case, it's only 0 in the strings. But the sum of moments or summatory of moment is always 0 in any point of the beam. I mean, if I cut the beam here and I look what are the moments in the left and right sides, it will be always 0. Well, that is a very good news because if I calculate the moment in this point, R1, I will eliminate R1. Why? Because moment is force multiplied by distance. I am at this point, R1 is separate from the place where I'm doing the calculation, 0 units. R1 multiplied by 0 is 0. If I calculate the moment here, I will have R1 multiplied by the distance, all forces. R2 multiplied by the distance where I am, 30 multiplied by the distance that is 0, 30 disappear. Well, if we calculate the moments in the extremes, in this case, or let's tell instead, in the place where R1, R2 are located, we can eliminate R1 and R2. Because again, the sum of moments is equal to every force multiplied by the distance that separates every force acting in that object in the place where I am calculating that particular moment. Well, let's do it now. Let me clean here. Let me go back to the other exercise, sorry, and start doing that. Well, let's start. First, I will write an X, do the process like I do it. And now I will go from this point to the right, there is nothing. When I go to the left, there is nothing. I go to the right and I look all the forces. Let's start by here. The summatory of moments in the point R1, where I put my X, is equal to, first, I have a force of R1 multiplied by 0. because the distance that separates this vector R1 to the place where I am is 0. This tends to be 0, disappear. I continue moving, and I have a force of 30. 30 multiplied by the distance, that is 2. Look, I will write that 30 is negative. Why? Because it's a vector that is pushing down. I decided that. I decided that every vector that go down is negative. Every vector that go up is positive. You can do the contrary, and the result will be the same. In my case, it's minus 30 multiplied by the distance, that is 2. Nothing happens in the beginning. Imagine that you are like an ant, and you're walking there, and there is nothing until you arrive to the end, where you have R2 multiplied by the distance that separate R2 to the place where you are. That is where I put the x, 12. Now, we have one equation, and R1 disappear. We have only one unknown. We can take out this from the equation. What we do, we just write R2, and we move all the elements to the other side of the equation. 30 multiplied by 2 was 60. R2 multiplied by 12 is equal to 0. I take R2, move the other elements, 12 go divided, minus 60 became 60 and go up. Well, 60 divided by 12 is 5, and that is the value of R2. I already got R2. When I go R2, I can go how much is R1. It's very easy. Look, R2 was 5. The force up is 30. How much is R1? It needs to be 25. But in this case, it's an easy exercise. We can do that. We can tell the summatory of forces, is, the vertical forces is 0, and that's it. But I don't recommend to do that. I recommend to repeat the process, because in some complicated equations, you will make a mistake, and you will not be sure that you did a mistake, and you will do all the exercise, and all the graph and everything that you need to do will be grown, and you don't want that. Well, my recommendation is do the process again and calculate the moment in R2, and let's do it. I put an X here, and I write, this is R2. Summatory of moments in R2 is equal to R2 multiplied by the distance, that is 0, disappear, bye-bye. Nothing happens until I arrive to 30. I will tell that everything that goes down is negative. In this case, just in this being not always is like this, 30 multiplied by 10, 10 is this distance that separates me from there, and plus, because it's up, R1 multiplied by this distance, that is 12. I can take out R1 from the equation, like I did before. 30 multiplied by 10 is 300. R1, go here, 300 pass up. 12, that is multiplying, now divide. R1 is 25. I want to make sure now that my answers are okay. And I can do it. Look, reactions are equal to the loads, because vertical forces are 0. Or every vector that push down plus every vector that push up will be equal to 0. That is our point. That is what we are supposed to do. Well, the case here is the same. I have R1, let me go and draw that. I have R1 is a vector of 25. I have R2, a vector of 5. I have 30 that is going down. I put all those vectors together. 30 is equal to 30 is correct. Now I can write reaction 1 and reaction 2 here and start with the second part that we will do next week. Well, in order to be clear, please understand, when you calculate the moment in R1 and you put an X, you eliminate R1 and you find how much is R2. When you calculate the moment in R2, you write an X in R2, you eliminate R2, you already have 30, but you calculate how much is R1. And you write that in order. R2 will be in this point, R1 will be in this point. Don't get confused. Now, let me go with the second exercise. The second exercise is very similar to this one, but we have two forces. Before we have 1 of 30, now we have two, 1 of 20 and 1 of 10. It's exactly the same process. In order to do this calculation, I know that I have 4 vectors. 2, I already know the value, and 2 R1 and R2, I don't know which one is the value. I will tell myself that those are negative because are pushing down, and this is positive because it's pushing up. In this case, why? Because whatever calculation I will do, in whatever place I put my X in R1 and R2, all the forces are in the same side of the reaction. That is not always the case. But for the moment, everything that goes down is negative, everything that goes up is positive. Clear? Okay, let's do this project here, this exercise. First, I write an X in R1. I like to start by R1 always. You can start by R2, but I like to start by R1, and I write R1 multiplied by the distance where I am is 0 by R1. 20 is pushing down, is negative. Multiplied by the distance that's separate in the place where I am, that is 2 units. 20 multiplied by 2. Why? Because I am calculating moment. Moment is force multiplied to the distance from the force to the place where you are doing the calculation, where you are calculating the moment. Next, I move here and I have 10. 10 is negative, multiplied by the distance. The distance is 6. Finally, there is nothing else until I arrive to this vector that will be positive plus R2 multiplied by the distance that is 12. The total length that separates 12 to the place where I am. I take R2 from the equation. 40 plus 60 is 100. R2 is equal to 100. Now it's positive because move to the other side of the equation. R2 stay there, 12 move to the other side and is divided. R2 is 8.3333. Ready, we calculate R2 after calculating the sum of moments in R1. Again, remember, I am not calculating the moment in R1. The moment in R1 in this particular case is 0. But I am calculating the sum of moments in R1 that will be always 0. In any place that I calculate the moment, any place, can be here, can be here, can be there, can be there, the sum will be equal to 0. If not, the moment, the beam will start rotating, and we don't want that. We depart from the principle that the beam will not rotate. Let's do this second one. Well, I go, let me clean all this. And I write an X in R2 and I do the same. Summatory of moments in R2 is equal to R2 multiplied by the distance that is 0 is 0. Walk in the beam and find an element of 10. Okay, we have 10 there. 10 multiplied by the distance is 6. It will be 60. I continue walking. 20 multiplied by the distance that separates in this case is 10. And finally, R1 multiplied by 12, that is positive, equal to 0. I resolve the equation, and R1 is equal to 21.66. I want to make sure that this is okay. Well, I put R1 plus R2, that are two vectors pushing up. And the total is 30. And it's true that the other two vectors pushing up, 20 and 10, is 30. 30 equal to 30. This is correct.